Okay, we're going to talk about how to calculate the center of mass. So let's start with the definition, which is given here. The position vector for the center of mass is defined as 1 over the total mass times the sum of the individual position vectors of each mass element that you have. And so that's a vector. It has coordinates, x, y, and z coordinates to it. And of course, if our mass is continuously distributed instead of individual masses, then we would convert that sum into an integral. So the integral of the r vector dm, so the individual mass elements. So as I said, this is a vector. It has 3 components, so it's in principle 3 equations. 1 over mass times the sum of the x positions times the mass elements, the y positions, and the z positions. So 3 equations in that one expression. And again, of course, if we have continuous masses, these sums would turn into integrals. So the integrals we're going to be doing are the form 1 over total mass, sum of position, x, y, or z, and differential mass elements. And so that's really the problem. Really the problem we have is in solving center of mass problems is finding dm. Right? That's the question in almost every case, is what should the little mass element be in our problem. Alright, so in 2D problems, we know that dm is going to be some kind of a density times an area. So then it comes down to what's dA. Right? So the problems are going to come down to how do we express the area element in our various problems. So as an example, let's see if I can do this. Suppose you have a shape like this, right, in XY coordinate system. And so what do we mean by dm? We mean a little chunk of this piece, like so. And so dA is this little square here. And in Cartesian coordinates, we would just write that as dx dy. If we had a different shape, we might find that the polar coordinate system would be an easier coordinate system to work in. So still, we have to figure out what our little dA is. It's just a little element of area in whatever coordinate system we're working on. And in the polar coordinates, that dA would be r dr d phi. Right? So in principle, the idea is figure out what your dA is, and then you're just going to integrate over it. And so in this 2D case, we're integrating over x and y, so we would have a double integral. So let's say something like this, that sort of have to integrate dA, which would be a double integral over dx and dy. That's the sort of thing we're thinking about. Okay, so let's think about this in the context of this problem here. So let me just redraw this here. Alright, so if that's what our shape is, so we've got our little chunk of dA, and I'm saying that we're going to integrate that in both the x and the y directions. Well, let's think about what doing that integral in the y direction would be for this shape. That just means integrating this way, integrating this little square from one boundary to the other of our shape. So it's really getting this little strip right here, right? And so I can kind of do that integral in my head in a sense. And so what's the dA of this strip? It's dx, the width of the strip, times the height of the strip. And what is the height of the strip? Well, it's just this function y. If you characterize this upper surface of this shape as having a function, maybe I'll call it y1 of x, then the shape of this area is y1, the height of this little strip, dx. Okay, so now in order to do my integral, to integrate over the whole shape, all I have to do is take this strip and integrate it, right, from x equals 0 to x equals something, let's call it b. Right? So I'm just going to add up vertical strips of this nature, all of who have an area dx times y of x, and that's what I'm going to add up going across this shape. Now, an alternate way that you could break this guy up is you could imagine doing it this way. Instead of vertical strips, let's imagine you do horizontal strips, like so. All right, so this dA here, well, let's see. Oh, well, look, one question that arises right away is that my strips are going to be different whether I'm in this region here or if I'm in this triangular region up here. In principle, these strips are going to have a dA of height dy, and then what's their width? It's, you know, this position here, so that's an x value, that's x of y. So this is, I'll call it x1 because it's the inversion of this function. If I gave this line as y1 of x, then I just have to invert that around and solve for x as a function of y, and that gets me the x coordinates of this line along here. And this area element here is going to be dy times x. This one's a little bit easier in a way because it's just going to be height dy, and then it's the x value here, which we said was going to be b. This is sort of sliding off the edge here. Okay, so we could also break this area up into horizontal strips, and we notice that in this circumstance with this shape, there are actually sort of two regions of the horizontal strip that we have to keep track of. So that kind of issue is going to come up, and that can happen also in your vertical strip case sometimes as well, so we just have to be aware of that. Okay, so let's look at a slightly more general case. Draw something like this. Let's get our axes. Oh, that was terrible. Let's get our axes here. And let's say I've got a function that sort of looks like this. And one that goes like this. So this would be sort of a pretty general case where I have a function y1 of x that defines one boundary of my shape, and I have another function y2 of x which defines the lower boundary of my shape, and this is the shape that I want to find the center of mass for. Alright, so like I say, what we're going to think about is dividing this up, finding my little area elements, and first dividing this up into vertical strips. I'm going to sum up over this. So let's see how we use that to find the center of mass. So I'm going to find the x coordinate of the center of mass, which is 1 over the total mass times the integral of x dm. Right, and what I'm calling dm in this case, dm is going to be a rho dA. And if I assume that I have uniform density, which is almost always going to be our assumption, then this is just a constant, and I can pull it out of the integral. So I'll get rho over m total. And now, what am I going to do about this dA? Right? In principle, like I said, it would be a dx and a dy. So let's just stick that in there. So I'm going to do an integral of x dy dx. And so got two integrating over y and integrating over x. Okay, so let me write this down here in the next row. I already made rho constant and pulled it out. And so I have rho and rho. I'm going to think about doing that dy integral first, right? Which is going to be going from where to where? Well, y2 of x to y1 of x. And I'm integrating x, which doesn't have anything to do with y, so that can come out of the y integral. So in some sense, right, I have these two integrals, an inner integral and an outer integral. Now you recognize that this integral here, right, if I integrate dy from one place to another, this is just going to get me y1 minus y2, which we would recognize as just the length or the height of this vertical strip. So just like I said on previous page, we can, instead of sort of starting from little squares, we could actually just start from the strip. So I could do this for sure, but I might, instead of starting way back here, I might just say, hey, look, what I'm doing here is I'm going to integrate x, and I have dm. So what's dm? It's going to be rho, and then what's the dA for this vertical strip? It's dx times y1 of x minus y2 of x. That's my dA. So I'm sort of doing this integral just sort of in our head, just by inspection of the figure. So that plunks us right down here, right? And so I can clean this up a little bit. Again, the rho, the constant comes out. It's an integral of x times y1 of x minus y2 of x dx. From, and oh, from where? So where's my x going? Where's my x integral going from? It's going from a to b, so I can put limits on that. All right. Cool. So then this is the integral I'd have to do, right? So now I have to have these functions y1 and y2 of x, and they're functions of x. So these are going to be functions of x that I can stick in here and I can integrate, right? So now the problem, I need to do a specific problem where I'm given those functions and I've got an integral to do, and we hope and pray that we can do that integral. If we can, we get the x coordinate. All right. What about the y coordinate? Sun there, that's nice. All right, so what about the y coordinate? I'm going to do something similar, so let's just get definition. The y coordinate of the center of mass is 1 over the total mass times the integral of y dm. All right? And in this case, for the y coordinate, if you look back on this picture here, right? Why did I use vertical strips when I was calculating the x coordinate? Because for each of these strips, that whole strip has a single value of x, right? And what I'm integrating is, what is the x coordinate of a chunk of mass? So this whole chunk of mass has the x coordinate value x, right? And then this vertical chunk has a different x value. All right, so if we sort of think about doing the same thing in the y, so put this in the corner here to remind us. And going from A to B, and we've got some shape like this. Right. So here, if I want to do the same sort of idea, I need to have horizontal strips, like so that this whole strip has a value of y, right? A single value of y that I can stick into this integral. So here, my dm would be this, rho dA. Right, but the dA I want to consider are these horizontal strips.